pi, and then you add this is the same result, just in terms of interior angles versus exterior. And so here's the proof. The proof is actually pretty easy to follow, this part of it at least. So like I was saying, we define E1 to be the normalized partial velocity in the u direction for the parameterization. E2 is defined to be JE1 in the sense that dm acting on E1, E2 has to be 1. So this two-form equation uniquely defines E2, because if you look at a two-form, you got two dimensions. There's only one choice which will make a non-vanishing two-form work out to 1 once you've already given E1. Like that equation uniquely defines E2. And we call it J of E1 for, because that's what it means geometrically. It's a rotation by 90 degrees with respect to the local geometry. But anyway, second structural equation, d omega 1, 2 is minus the Gaussian curvature times theta 1 wedge theta 2. But theta 1 wedge theta 2 is what we call dm. All right? And as such, we notice that we have that d omega 1, 2 plus k dm is equal to 0. All right? So then I can integrate that over the surface and get 0. But notice that I'm integrating d omega 1, 2 over the segment by the generalized Stokes theorem. That's equal to the omega 1, 2 form integrated over the boundary of the segment. So I guess technically speaking, we're using generalized Stokes theorem with corners, which is proved in Lie, I think, maybe. Yeah. Let's say it is. And then, anyway, so we have that plus that. But what is that? Well, that, followed by the lemma on the next page, works out to the integral of the Gaussian, the geodesic curvature, plus the sum of the exterior angles minus 2 pi. And it's just a gory case-by-case analysis as you go around the two segments, like I'll show you. So essentially, we'd have the theorem if we know that that circled thing is equal to the boxed thing, right? So if we can just prove that, then we got it. The proof that the integral of the connection one form is equal to that rests on integrating the connection one form on each segment. But remember, by the thing I have written over here, although if you look at this, we can solve this for the integral of the connection form. It gives us the integral of the geodesic curvature, minus the difference of the angle function, right? So like, so see how that goes? So like the integral of omega 1, 2 over alpha is minus the difference of phi b. Now why is it b and a? Because b and a, remember, alpha uses u as its parameter, which means it goes from a to b. So a and b are respectively the starting and ending parameter for alpha, like so. And then I have that. Now, but what's the angle between E1 and alpha prime? What is alpha? Alpha is nothing more than using u as a parameter. So alpha prime is collinear to E1, because E1 is by definition that. So that makes phi of A and phi of B here both very, very boring. They're 0. They're just 0. So like I said, this is equal to that, because this is the picture. Alpha prime and E1, they're the same. What comes up next? Well, beta. So the picture for beta is something more like the V. Beta goes along the V direction, right? Which doesn't have to be the same as JE1, by the way, But anyway, the point is the angle is not automatically 0 or anything. And, but if you look at it, you can work out the angle here I'm too close to it though. So my claim over here is phi of C minus phi of D is this. I'm not sure. Phi of C. Well, I'm saying phi. Yeah, well, I do mean phi. It's the angle between, so phi is the angle between E1 and beta prime. That's this angle. So the angle between E1 and beta prime, that is what we define to be E2. So that's phi of C is indeed epsilon 2. And then the angle between E1 and beta prime up here is not E3, but it's supplementary, thank you, to E3, epsilon 3. So we need pi minus E3 for that angle. Phi of D is pi minus epsilon 3, like I wrote there. So that gives us epsilon 2 minus minus is a plus, minus pi. That's the integral of omega 1, 2 on that segment. All right. And let me go on here. And you do a similar calculation for segment 3, a similar calculation for segment 4, and you add them all together, and guess what happens? You get all of this. So nothing from the first epsilon 2 plus epsilon 3 minus phi, like we talked about. The next segment actually, again, because it's along the curve parameterized by alpha, again, the angle of incidence is not interesting. Or maybe I think they may both be pi in this instance, and they cancel out. And then finally, the last one is a little bit more interesting, but it's similar to the one we looked at. And so if you look at it, you end up with the sum of the exterior angles minus 2 pi, which is what we've set out to prove. Now, this is a joke. I have forgotten exactly what it was about, but at the time I made this course, other classmates of Min were harassing him about something being a door or not, so I just built a door into the lecture.
Was it like the debate about whether more doors or wheels?
More doors or wheels? It could have been for, I was not privy to the conversation. I just know that they were arguing about doors, so I just threw a door into my lecture to be annoying.
There was a thing a couple of years ago where a lot of people were arguing about whether there are more doors or wheels in existence.
More doors or wheels in existence?
People get very abstract with it to try to argue their case.
Jeez. What if the wheel is a door?
Like, is this a door?
That whole thing is a wheel.
I said that the electron orbitals going around atoms were wheels.
Electron orbitals are wheels. That is very silly. Okay, so every compact surface has a rectangular decomposition. So what does that mean? Basically, you can take a surface that's compact, and you can basically chop it up into like little rectangular bits, such that the union of those curved rectangular bits is the whole thing. That's the claim. Now, proving that, well, he says the proof is by scissors. If you look at page 369 of O'Neill's book, you'll see a proof there. But a remark I should make, if you have a diffeomorphism from M to N, which means smooth and smooth inverse, that implies that F is a homeomorphism. But the converse is generally false. A homeomorphism does not imply diffeomorphism. That means the following is a bit surprising. All right, let's see here. So, well, we're not quite to the part that's surprising yet, but here's the theorem. This is a result from topology. It says if P is a rectangular decomposition of a compact surface, and V, E, and F are the number of vertices, edges, and faces of the decomposition, then the integer V minus E plus F is the same for all such decompositions. And moreover, this integer is called the Euler characteristic, like so. So this is one of the most famous early results in topology. This predates most of the rest of the field. This was, you know who Euler was? He's a 18th century mathematician, and this is his. So this and the bridges of Königsberg problem, some of the very first things. This vexes me. So and that is the same Lee. John Lee has a book on Riemannian manifolds, and in that he has this really nice, about 5 pages, on polygonal decompositions of surfaces. And I have scanned that. I have a nice PDF of it that I gave to this class, and it's nowhere to be found. But I do have the book at home, so if I find it, I'll make a scan again and give you guys it, because it is, it's nice to see, because some people use rectangular decompositions, other people use triangular decompositions, but it's kind of just a choice. Like a triangular decomposition is also called the triangularization of the space. So a triangularization of the space is basically, taking the space and finding curved triangles which fill it out, So for example, the sphere is triangularized, triangularization of the sphere is given by the tetrahedron. If you can imagine it having rubber sheets, and imagine that it's just inscribed inside like a basketball, such that the edges hit the basketball, and then you can somehow blow up the tetrahedron, it would just conform to the basketball, So this is because you can expand it into a sphere. It's a triangularization of the sphere. And so like here's a good example what the Euler characteristic is talking about. The number of vertices, 1, 2, 3, 4, is 4. Number of edges, 1, 2, 3, 4, 5, 6 edges, right? Number of faces, 1, 2, 3, 4 faces. So this makes the Euler characteristic of the sphere equal to 2. All right? Now, you can also talk about a cube. So a cube has what? 1, 2, 3, 4, 5, 6, 7, 8 vertices. It's got how many edges? Apparently 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And 6 faces. The Euler characteristic is 2. That makes sense because that's a triangularization of the sphere. This is going to give you a rectangularization of the sphere. If you were to blow that up, you'd get back to the sphere. The torus, on the other hand, has an Euler characteristic of 0. As I said, I don't see it yet. Well, we don't have time. So, cool thing, if you add a handle to a compact surface, it reduces its Euler characteristic by 2. I guess if you add a handle to a sphere, does that make it a donut?
Yeah.
So it makes sense that if the Euler characteristic of a sphere is 2, the Euler characteristic of a donut ought to be 0.
Is anything That's two.
Anything with one hole a donut? Any smooth surface with one hole a donut? I don't think so, because I think it has to like close back in. Yeah, it has to have to be a donut, you have to be able to get stuck this way, but also that way, I think. But I'm sure there's an abstract definition of donut which would give a different answer to this question. Anyway, so theorem 6.8, if you have a compact connected orientable surface, there's a unique integer h greater than 0 such that m is diffeomorphic to a sphere with h handles attached. So you can do this kind of surgery on spheres. We talked a bit about surgery earlier, I think. Did we? Or am I thinking of a different semester? I think I might be thinking of a different... Oh, briefly? Okay. So compact orientable surfaces M and N have the same Euler characteristic if and only if they're diffeomorphic. Now finally, we come to the proper statement of the Gauss Bonnet Theorem, which simply says that the total Gaussian curvature of a surface, which is of a compact orientable geometric surface M is 2 pi times the Euler characteristic. And the proof of this basically rests on taking the surface, paving it with 2 segments, meaning that, you know, that's just essentially a rectangularization of the surface. And then the integral of kdm breaks into the integral of each one of these. And then when you sort through the sum of the exterior formula, it rewrites in terms of the VEF formula. It's what happens. And I have some of the details here, but I always get confused on these details, so let me not belabor them too much here. I want to get to the triangle thing. But this is, I mean, here's some of the details. Essentially, the thing we just had about 2 segment, the integral of the Gaussian curvature over the 2 segment gave us this. And then you add those all together. One of those gives you the 2 pi f, and the other piece gives you this v. And so you can factor the 2 pi out, and you end up with the, the formula for the Euler characteristic. There is some counting there that I'm a little fuzzy on. The claim that I always get stuck on is that 4 times the number of faces has to be 2 times the number of edges. This is something that's, I think, generally true. It's true for this rectangle, but why is it true in general? Involves some counting that I'm a little fuzzy on. I'm not saying it's hard, I'm just saying I'm fuzzy, yeah.
I have to go soon.
Okay, we're almost done. And so so the proof is very close to what we did. So the thing you guys have been waiting to see is right here. So this is Gauss Bonnet Theorem for an oriented polygonal region in a geometric surface. It says this. So this becomes more interesting if you have a polygon which all the edges are geodesics. Then the geodesic curvature is 0 on those, and so that term drops out. And then you just have the integral of the curvature over the polygon is equal to plus the sum of the exterior angles of the polygon is equal to 2 pi times the Euler characteristic. And so if you have a triangle, for example, in a oriented geometric surface, then you have this, because there's only 3 exterior angles, right? Or the sum of the interior angles minus pi is how that goes, because you get, you know, minus 3 pi, 2 pi minus 3 pi is minus pi. So if you have a geodesic triangle, right? Geodesic triangle, then you have the integral of this is equal to that. So let's see here, what happened to the, yes. So in particular, this becomes, if you have a constant, if you just have constant curvature, right? What you have is that the Gaussian curvature times the area of the triangle, right, as defined by the area given by the metric on the surface, is equal to the sum of the interior angles minus pi. So in the case that your curvature is 0, this reduces to Euclidean geometry. The sum of the interior angles is pi. But if you're in positive curvature, the sum of the interior angles minus pi is somehow related to the area of the triangle. That's really weird, right? But that's how it works. So like, standard example I always think about is like an eighth of a sphere, where you have, like, that's a geodesic triangle because the great circles on the sphere are the geodesics, right? So if you think about, like this, you know, this guy right here, you've got a right angle, you've got a right angle, you've got a right angle, you got, you know, 3 90-degree angles. The area is 1/8 of 4 pi r squared. What's the curvature? We worked out the curvature of a sphere of radius r. The curvature of a sphere of radius r, Gaussian curvature, was constant, and it was equal to 1 over r squared, right? So sort through that. The area of this is 1/8 of 4 pi r squared, right? So what happens when you multiply those? That would be k times the area. We got 2 pi? Is that right? 4 pi over 8, what's that? Oh, pi over 2, duh. And what, so you got pi over 2 is k times a. What do you have here? Sum of the interior angles. Pi over 2, pi over 2, pi over 2. 3 pi over 2 minus pi, pi over 2. See, it works. But if I was to make a smaller triangle, I wouldn't have the same angle excess as I do here. And likewise, if you have negative Gaussian curvature, it could look like this. You could have the situation where the sum of the interior angles is less than pi. And like I said, I tried, but now if it's not but you notice that if the triangle is not having sides which are geodesic, it's more complicated than just that, because you actually have to calculate the geodesic, the integral of the geodesic curvature along the arc length of the triangle would also come into play. But geodesic triangles are the most interesting ones, which we can make a straight analogy to, this. And anyway, this is the first and most interesting, perhaps, theorem that relates differential geometry and topology. See, because the Euler characteristic is very much a topological thing, whereas the Gaussian curvature is very much not. It is something that's derived from the geometry of the surface and integrating over it, right? And anyway, like I said, it's an active question of research whether or not we can find similar theorems in higher dimensional contexts. There are some results already known, but that's all I can do for this course. So, thanks, guys. Thank you.